Okay, so hello everyone. Welcome to lecture 7 for Stat 310. Just a reminder that homework 2 is due Thursday, September 17th. Let me know if you have any questions about that. So just to go through what we're going to cover today. So the last few lectures we've focused on chapters 6 and 7, and so I just wanted to take a quick step back and just kind of review that material in the context of our general framework, just to try to put everything into context. And then we're going to move on to our next chapter, which we're going to spend maybe a couple of weeks, maybe 2 to 3 weeks on, which is chapter 8, which is a very important chapter on parameter estimation. And in particular, today we're going to go into the sampling distribution. So we're going to focus mainly today on 8.1, 8.2, and parts of 8.3. And so that'll just be kind of an introduction to chapter 8. And we'll try to look at kind of what we're doing differently in this chapter compared to what we've already done in previous lectures and in chapters 6 and 7 of the textbook. So as I'm going to frequently do, I'm going to go back to this general framework that we have, which has these 5 components. So remember that we always have this kind of sample data, x1 through to xn. So this is really the sample that you're kind of seeing. And then we typically will have a distribution of the x size and some parameters of interest that we're trying to guess, whether it's the probability of voting Democrat or some other way, or whether it's the mean of some distribution. There's some parameter that we're interested in. Then there's going to be some statistics or estimators, which are functions of the data, like the sample mean or the sample variance. And then then the next part of the component is the distributions of those statistics. So sometimes they're exact, but often, and we'll see that, we saw that in chapter 7, and we're also going to see that in chapters 8 and 9. They're typically going to not be exact, but we can usually use some asymptotic results to do some sort of inference. And then the 5th step is really where we use everything from the first 4 components to actually try to address some inference questions. So like, what are the statistics in 4 tell us about the parameters? So the statistics from component 3 with distribution in 4 tell us about the parameters. And so we're going to see concretely what this has been in chapters 6 and 7 before we move on to chapter 8, just to see kind of how chapter 8 is a little bit different. So remember that chapter 6 really focused on independent normal samples. So there, we had our data here was x1, x2 up to xn. Okay. And then, so this is typically going to be our sample data. And then we also had the initial, we assumed that everything was kind of nice and just normally distributed and with the same mean and the same variance. Okay. And also that we have independence. So these are just independent draws from a normal distribution. So there's 2 parameters here, the mean and the variance, the population mean and the population variance. So statistics that came up in chapter 6, there was the sample mean. So this was kind of this is the sample mean, which we're going to see a lot in the next few weeks and throughout the course. Then we also saw the sample variance. So this was the sample variance. And then we also had this t, which we occasionally saw, which was, if you look at this is kind of the t statistic. And then if you look at the distributions of these statistics, we've seen many times that things are very nice when they're normally distributed because, you know, we know what the distributions of everything is. So the sample mean has a normal distribution with mean mu and variance sigma squared over n. Then we also know that the sample variance has this chi-squared distribution when you rescale in the appropriate way. And then if mu is 0, then we have this additional like nice result that t has a t n minus 1 distribution. So one thing to note is that all distributions are exact and hold for all n. Okay, so these are nice because these results are exact and not asymptotic distributions. And then, you know, this fifth component is really how do we use, you know, put together everything to kind of answer a question about, you know, any of these statistics. So, you know, for example, if we wanted to say something about, you know, if we wanted to infer something about mu, then, you know, you can use the fact that and this is in the scenario where sigma is known. You know, you can certainly just use the z-score, which, you know, you've seen in this class and potentially in other classes. And so, you know, okay, and then you know, if you want to draw if sigma is unknown, and we want to draw inferences about sigma, you can again use the fact that and so if we wanted to find confidence intervals for sigma squared, you essentially just say that you can, you know, use the fact that okay, and so this allows you to you use chi-squared n minus table to do this. And so you've had to do some of these calculations in the homework, so I won't go into the exact specifics of those calculations. You've hopefully seen that in the homework and potentially in section as well, but you can see how you know, you can find confidence intervals for sigma squared as well. And the other thing you can do is if sigma squared is unknown and you want to draw inferences on mu, you can use the t distribution. since we know that if you want to do inferences on mu, you can kind of see that if you subtract off the mu and divide by s over square root of n, that gives you Tn minus 1. So you don't need to know the sigma squared to calculate the any confidence intervals that you need. Okay, so that in a nutshell was kind of what was going on in chapter 6. So in chapter 7, if we look at the key components of the framework, so what we had here was we had a finite population. So you had, you can think about, a voting population where there's n people. N is the population size. And this is usually large, like very large, like it may be on the order of millions or something else. And so once again, your data is your sample data, x1 through to xn. Okay, and so then the question is, how do you kind of get that sample data from your population? So remember that your population is, as I've mentioned earlier. And so how do you get the sample from your population? So I should be clear here that n is the sample size, and it's always going to be smaller than big N. And so the parameters of interest here, there's two that we look at. There's more in the textbook, but in this course we're only covering the two, which is the population mean. So this is a property of the population. So it's let me use this J. Okay, and then the population variance, which once again is a function of the population. Okay. And what was kind of interesting and unique to chapter 7 was that we looked at two sampling schemes. IRS, or independent sampling, and that's when you sample with the replacement. And then the simple random sampling, which is sampling without replacement. So as we discussed in previous lectures, simple random sampling is probably what's more likely to arise in practice, because when you access one sample, you're typically not going to want to put that back into the population and then potentially re-access it again. So you typically are going to do sampling without replacement. But as we saw, the calculations for simple random sampling are substantially more complicated than for independent sampling because you didn't have independence of the XIs, and so you gain a lot more challenges in terms of the calculations. And so the statistics that we focused on again were kind of staying with the theme that we'd had in chapter 6, which is the sample mean. So remember that the population parameters are a function of the population, so they don't involve the sample data at all, whereas the statistics are functions of the data. Okay, so here we're looking at the, everything here is a function of the data. Okay. And then we spent some time looking at so the properties of x bar and s squared. So we noticed that E of x bar is equal to mu for both IRS and SRS, because that calculation doesn't rely on independence at all. And then we also have that, for IRS, the calculations are kind of nice and simple. We have that, variance of x bar equals sigma squared over n, and then we had the expectation of s squared is sigma squared, and that's why we have the little n minus 1 to make sure that estimator that the expectation of s squared is sigma squared, and then we also using the CLT, you can certainly say that we get things converging to a normal distribution, and so therefore you can use standard kind of ZT tables in this case. And the other thing to note is big N, the population size, plays no role. Okay. On the other hand, for simple random sampling, we saw that the calculations were substantially more involved. We get this same sigma squared over n, but then we also get this correction factor, which is it's clearly something that's less than 1, but you can see that if the population size is much larger than the sample size, then this gets pretty small. And then we also found that you get sigma squared, and then you get another little correction factor. So, and the upshot of this was that if we get, typically the regime that we're looking at is little n over big N is going to 0, basically. So, for example, if you're looking at a voting sample of 100 in a population of on the order of millions, that's going to be very, very small. So, so if we have that, n over n is going to 0, and n is going to let me just see. So IRS and SRS are very similar in terms of the results they gave. So we saw that the calculations were substantially more challenging for SRS, but in terms of the results, they're very similar if you've got little n over big N converging to 0. And then when we so when we do inference, and then, if n is close to n, we need to be more careful. Okay, so that's just kind of a recap of the what we covered in chapter 6 and chapter 7, and like in this general framework. So really chapter 6 focused on the case where everything's independent and normal, and chapter 7 focused on the case where we're looking at finite populations, but we're really only interested in two things, which are the mean and the variance. And so now we're going to try to be more general. So chapter 8 is it's more general problems. So we're looking at questions like, for example, if, we want to estimate and so lambda is kind of the average lifetime. Oh, that's actually the opposite. Lambda is the so in homework 1 you had questions about the arrival processes which had exponential distributions. And so if lambda is the rate of event, how do we estimate lambda? So current are so the current frameworks we've looked at, which were the normal samples and then the finite populations, they don't really apply here. Obviously, this is not a finite population. And more importantly, we're trying to estimate a parameter lambda that actually isn't the mean or the variance. And so the current frameworks are too restrictive because they only apply to mu and sigma squared. So so the big kind of question we're thinking about here is like, how do we estimate and do inferences for general parameters? So, we've seen like lots of parameters like lambda and p, and so lambda for the exponential, p for the Bernoulli, and for the geometric, and we've seen other parameters in lots of other distributions. And so what we're going to learn in chapter 8, and so over the next 2, 3, 4 lectures, is really going to give us this this general framework. So once again, we're going to start with a framework and kind of get to the, so I'm going to give you a preview of what's going to come, and then we're going to dive into the details for the rest of today's lecture, and then also going into the next few lectures beyond that. So once again, we start with the sample data x1 through to xn. So we're going to be pretty general here. We're going to assume that xi is just has some distribution. We'll use I'm going to use the notation f. So here, I'm using this notation. Maybe this is better. Let me just use this notation. Okay, so remember, so this is this could be like a PDF or a PMF or, any other way to characterize the distribution. We're going to typically assume that these are independent samples as well. And then the parameter or parameters of interest are theta. So they're the kind of parameters that we're trying to estimate. Um, and this is going to be theta hat, which is going to be some function of our data. Okay, and we're going to talk about how to do that. In chapter 8, we're going to see two really important examples. And then 4 and 5 we're going to dive into a little bit later. So we're going to, develop some rules for So we're going to develop some rules for finding asymptotic distributions for theta hat. Because we don't really know what those statistics or estimators are yet, it's a bit hard to talk about the fourth and fifth components. And so, yeah, like there's a few examples I want you to kind of keep in the back of your mind that we're going to go through, if not today, then in the next lecture, or if not in this lecture, in the next lecture, and in others to come. So, for example, so if we have a bunch of Poisson random variables, then we have that. The parameter that we're interested in is this this rate. So we've already seen this example through voting, which is this Bernoulli distribution. So your theta here is just P. I've already talked about. Once again, you have theta equals to lambda. And then, another example to keep in your mind, which we're going to go through, is, you might have uniform 0 theta, and then here your parameter of interest might just be theta, which is the endpoint of this this uniform distribution. Okay, and so our goal is to find general procedures to estimate theta and form confidence intervals. For theta. So the first key idea, which we're going to unpack a little bit today and in the next lecture as well, is this idea of a sampling distribution, and this is covered in chapters 8.2 and 8.3 of the textbook. So remember that So what I'm going to focus on discrete random variables for now because it's easier to get this message across. But you can certainly generalize this to continuous random variables, and I'll kind of talk about how we do that throughout. But for discrete random variables, we have this PMF, px of k, where k is in the range of x. Okay, and then we know that the PMF defines the distribution. In practice, we don't know PMF because if we did know the PMF, then there wouldn't really be any statistical questions to address. You could just use the PMF to answer any questions that you want about the expectation, the variance, and do any inferences that you want, which is what was covered in 309. In practice, so in 310, in the 310 setting in practice, you have data where you sample from this PMF, but you don't actually have this PMF. So the idea is that x1 through to xn is it has this distribution, this PMF px, and these are independent samples. And I'm going to give you an example just to keep in the back of your mind. So think about Netflix ratings for a movie. Okay, so the ratings can be 1, 2, 3, 4, or 5. I believe you can also give half stars, but I'm going to focus on the idea that everyone just rates a movie with one of these 5 integers. So you imagine sampling 1,000 users who have watched a film. So this isn't everyone who's watched the film, but we're going to look at a sample of 1,000 who watched the film, and we're going to assume that they're kind of independent. So so the idea here is that so what we have for data is the number of people who rated 1, we'll say it was 270. This is, again, just fake data. The number of people who rated 2 is 140. 97 for the number of people who rated it as a 3. And the number of people who rated it as a 4 is 228. And the number of people who rated it as a 5 is 265. And this kind of behavior of having more data near the endpoints is fairly typical. Not many people go on to rate and say that they're going to give a film a 2 or a 3. They're usually going to say, I really like this film, or I really didn't like this film. But obviously there's going to be some in the middle as well. So hopefully the total number, this should add up to 1,000. So this should add up to 1,000. So this data that I've shown here, it kind of seems like the PMF, but it isn't exactly that. So and you're typically going to get data in this form where it looks like a probability mass function, but it isn't exactly that. So we know that Netflix ratings are the range is 1, 2, 3, 4, and 5, right? And so So the population here is the Netflix ratings across I would say maybe hundreds of millions of people who use Netflix. So hundreds of millions who use Netflix. So the idea would be that if every single person who used Netflix watched that film and rated it, that's the population distribution. So so px of k is the probability x equals k, where k equals 1, 2, 3, 4, or 5. And that's really looking at the question is that, if I pick any one in the population at random, what will the rating be? Okay, and so observe independent random sample of 100 people. Okay. And so what we have here is that, you have x1, x2 up to x100. So that's your kind of sample. So you can think of this as being like the finite population setting, but and we're drawing a sample, and each person in the population can vote 1 through to 5. So we're assuming we're in the independent random sampling setting where, we have x1 through to x100. So I'll just say so it's like chapter 7 with IRS, and so this is our sample data. So what we observe in our data is actually what's known as the sample I'll say sample PMF or distribution. And so what that is that that is, I'm going to use this notation. This notation hat is something we're going to start to see a lot. I actually already used it for the theta hat earlier on as an estimate for the parameter theta. So this hat is really I'm trying to hit home the fact that that this is a function of the data. It's not a population parameter. So typically if I want a population parameter will have no hat. And then if I want a statistic or an estimator to estimate that, I'll often take that and then just put a hat as above it to denote the fact that it's a function of the sample, not of the population. So what we're actually observing is so let me just explain this notation. This indicator function is just, hopefully you saw it in 309 or the equivalent. Okay, so what we kind of observed in our data was the probability of the sample, like in the sample, or the sample proportion of people who rated the movie as 1 is 270 over 1,000, which is this should be 1,000 people. I'm sorry, which was 0.27. Okay, and so in general, the sample PMF is just and you can clearly see that, and this is something you do for all k in. Sorry, this should be the range of x. And so you can hopefully see that just like for the population, we get that everything should sum to 1. If you sum up all those proportions, they should sum up to the total number of ratings that you have, which is 1,000. So this should always sum up to 1. So, I mean, the key question, to think about, and what'll kind of be the basis for a lot of the calculations we do is, how close is p hat x of k to px of k? And so the reason why I'm starting with this is because typically the data that you observe is essentially going to be like the sample PMF or sample distribution. And what we can hopefully see is that this expectation of p hat x of k and what you can hopefully see is that the expectation of indicator is just the probability of the event. So the expectation of an indicator of an event A is just the probability of A, because the indicator is just a 1 if that event happens, and it's a 0 if the event doesn't happen. So this is just probability xi equals k, which is px of k. So in expectation, but they're not the same thing. And I think if there's one thing you should really take out of this lecture is to understand the difference between this sample PMF and the population PMF. So remember way back to the first lecture, I talked about the fact that in Theory 9, you typically started with a population where you kind of knew everything about the distribution. Whereas in this course, we're really going to start with data, which is, this like something like a sample PMF or something else. And then you're going to try to, infer the population PMF or PDF or something else from that data. And so here, we know that the expectation of the sample PMF is equal to the PMF, but they're clearly different things, because one's talking about what's happening over the whole population, which is the PMF, and one's only talking about what's happening in the sample, which is the sample PMF, which is typically the data that you're presented with. So now let's see how this is potentially useful in some examples. We've worked out what the sample PMF is in that Netflix example. We're going to return to that later, but I talked about another example earlier. So we'll go back to kind of a nice simple example, which is x1 through to xn's Bernoulli P and independent. So here, this is nice and simple because the range is just 0, 1. So then, we can clearly see that there's two things here, which is the p hat x of 0 and then p hat x of 1 here. So by definition, p hat x of 0 is just it's the indicator xi equals 0, and p hat x of 1 is just 1 over n times xi is equal to 1 by just by definition. And then we know in the population that px of 0 is 1 minus p, and px of 1 is p. So we want to use the sample PMF to draw inferences about the population parameter p. So one thing we know is that we could just use p hat x of 1 is equal to 1 over n. The indicator xi equals 1, and because this is Bernoulli, we can just write this out as just the sum of the xi's, right? Which is just the sample mean. So we're kind of very fortunate that p hat x of 1 is just x bar. And then we also know that px of 1 equals p. We can simply use the sample mean, x bar Okay, and so this is something we actually did way back in the first lecture. So what we've kind of revealed here through the sample PMF is not very groundbreaking, but why it's useful is it just reinforces one of the ideas that we've already had, which is that, if you've got a Bernoulli distribution and you want to draw inferences about the proportion, so the proportion of people who vote in a certain way, you can just look at the sample mean. So if you start with the sample PMF, which is very easy to formulate because there's only two different values that takes, the sample PMF basically is like, it's essentially just x bar and then 1 minus x bar for px of 0. And so that is the way that you draw inferences for p based on your samples. So so it just kind of reinforces what we already know. And this is kind of a unique case, though, as we'll see shortly, because there's only one parameter and the range of x is only 2. There's only two different values of the range of x. There's 0 and 1. We're going to see that when the range of x is bigger and you want to actually tie things to parameters, things get a little bit more interesting, and that's what we're going to look at now. So let's look at the next example. So we're going to look at the case where our data here has a Poisson distribution here. So we know that the range of x for a Poisson is just all non-negative integers. And we also know that the Poisson distribution has this population PMF. Okay, now as we know, the sample PMF given by this definition. So the definition of the sample PMF is indicator xi equals k. And then the question that we want to think about is how do we use sample PMF to estimate or draw inferences about lambda. So remember that we know that px of 0, we can kind of plug that in and see that that's e to the negative lambda. We can see that px of 1 is e to the negative lambda times lambda. Px of 2 is e to the negative lambda squared over 2. And we can kind of continue this on. So one option, so one option to consider is we know that we can work out from our sample what this p hat x of 0 is, the proportion in our sample of samples that are 0. And then we can say, well, we'll let lambda hat, which is the estimate for lambda, be just equal to negative log of p hat x of 0, right? Because, since so but then, by the same, and, this is a perfectly reasonable estimator. So this is a perfectly reasonable estimate. But, think for a second about whether this is a sensible or a good thing to do. I'd say it's not totally not sensible, but one thing to notice is we're ignoring a lot of data. i.e. we're ignoring when xi is equal to 1, xi equals 2, etc. because we're only looking at, the first term in the sample PMF. So we're ignoring a lot of data here. And so so how do we use all of the data to form an estimate of lambda? And this lends itself to kind of the first, a very key kind of principle that allows us to essentially translate things between the sample and the population very, very naturally. So let me just kind of write this out. So we have in our population, we have the PMF, px of k, and then we also have the parameters, and we're going to use this notation theta. And then we have our sample, which is, we have the sample PMF, p hat x of k, and then we have our estimator or statistic. and we're using this notation theta hat. So the general idea behind the plugin principle, which we're going to see in this lecture and the next couple of lectures, is that you can express theta as some function of px of k, and then use this relationship to learn theta hat from p hat x of k. So another way to think about it is you have, your population here, and then your sample here. And so you don't know what's going on in the population. So you're trying to guess what's going on in the population, and you have your sample to do that. But you have your px of k here, and then you have your theta here. And then you kind of know this relationship between theta and px of k. We're going to see what that is. So let's just call this, some function. Let's call this some function h. And then in our sample, we don't really. What we want to do is go from this sample PMF to this theta hat, and so we want to guess what that is. And so what if you just use the same h again here? Okay, and so that's what we're essentially going to use, and that's going to allow us to kind of complete this loop of going, like trying to draw to get an estimate theta hat, which tells us about theta. So that's kind of somewhat abstract, but just to tie it to this to this example. So if we know that x1, so if we know that we have Poisson data, and so what can we say about lambda? We know that lambda is equal to the expectation, is equal just to the expectation of x, which equals to, summation k equal k in Rx, k times px of k, which is equal to okay, so we can see that this is kind of the, all right, let me write it this way. If we want to find lambda from the px of k, you can kind of use this this expression. And so similarly, if we want to find lambda hat, sorry, let me just wait a second. And okay, so I think we're gonna stop the lecture there. Sorry that it's about a minute or two to go. So I'll stop the lecture there, and we'll return to this discussion next time. Okay, so sorry about that slightly abrupt ending, but we'll get back to this in the next lecture. Okay, thanks very much.